Okay, so today we're going to talk about applications of integration. Last video we talked about properties of integrals and how to evaluate integrals and use those properties to solve different questions. And today we're going to kind of expand on that idea and go through some basic properties to start and then go through a few example questions. So let's start with some basic properties of integrals that we're going to kind of see today in this lesson. Let's say I have the integral from a to b of some function f of x. Let's call this a, and this will be b over here. We know that the value of the integral is equal to the area under the curve. But one thing we can do here is we can actually split this integral up into two separate integrals, where we have the integral of this region here, which we're going to call the integral from a to b, or sorry, a to c of f of x dx. And then we're going to add to it the area of this region here, which we're going to call the integral from c to b of f of x dx. So you can kind of split up the integral into two parts if you have a number in between the limits of integration. In this case, c is in between a and b. All right, second property. If I want to determine the area between two curves, so let's say we have a function here, and here's the upper limit of an upper function, and let's say there's another function that comes below, and let's say it looks like this. And we'll call this a, and this will be b. If I want to find this area, the region in between these two curves, what I'm going to do is take the area is equal to the limit, or sorry, the integral of a to b of the upper function minus the lower function dx. So it's always going to be the upper function minus the lower function. And then our third and final property, before we start getting into some practice questions, is imagine we were to take this function here, this region A, and rotate it around the x-axis. So now we're going from an area to a volume. The volume generated is equal to pi times the integral from a to b of the upper function squared minus the lower function squared dx. And so this is the washer method. If it was just one function rotated around the x-axis that was attached to the x-axis, and we'll see this, we'll see a problem like that today, you actually don't need this part because the lower function is technically 0. So this is kind of, this formula right here is a generalized form of the disk method. Okay, let's do a practice question. Okay, our first example. Let the integral from 1 to 5 of 3 times f of x dx equal 12. We're going to show that the integral from 5 to 1 of f of x dx is equal to negative 4. So the first thing we're going to do here is we're going to use a few properties of integrals. And the first property is that if you have a constant that is a term that does not have an x in it, inside the integrand, you can factor that constant out of the integral. Which we can then help use to simplify this. So the 3 will come to the outside, and we can, this is really a 3 times the integral here. And so then we can divide by 3. So the integral from 3f of x dx is equal to 12, then the integral of just 5, 1 to 5 of f of x dx is equal to 4. Okay, and using one more property, which is that when we switch the limits of integration, it will change the sign of our integral from positive to negative in this case. So now we've proven that the integral from 5 to 1 is of f of x is equal to negative 4. All right, letter B is going to be, this is letter A. Letter B is going to be a little bit trickier. because we're going to have to use a few more properties. If I have the integral from 1 to 2 of x plus f of x, I'll put parentheses around here, dx, plus the integral from 2 to 5, x plus f of x dx. We want to evaluate this. Okay, so the first thing we can do here is we can think of this, we can sort of like distribute the integral statement to both of these terms. And so we're going to rewrite this. We're going to break this apart into two integrals. So instead of writing the integral of x plus f of x, we can do the integral of x plus the integral of f of x. In this case, from 1 to 2. And then 2 to 5 is going to be our next one. So we've broken each of these integrals up into two separate integrals each. Okay, now we're just going to kind of rearrange this a little bit. I'm going to move the order of these around. We're going to group these together. So now this becomes the integral from 1 to 2 of x dx. That'll stay the same, plus the integral from 2 to 5 of x dx, plus the integral from 1 to 2 of f of x dx, plus the integral from 2 to 5 of f of x dx. Okay, and the reason why we're doing this is because we can use that first property that we talked about at the beginning of the video, and we're going to kind of go backwards, meaning that we can take this and we're going to bring it back in terms of one integral. Okay, so we're breaking these integrals apart, and then we're going to bring them back together. Because if the integral from 1 to 2 of x plus the integrals from 2 to 5 of x, well, we can rewrite that as the integral from 1 to 5 of x dx using that first property. And then similarly over here, this becomes the integral from 1 to 5 of f of x dx. Okay. Well, the integral of 1 to 5, from 1 to 5 of x is going to be the value that we get when we evaluate x squared over 2 from 1 to 5. So we're just going to evaluate that normally. We don't know what x is, or f of x is, but we do know that the integral from 1 to 5 of f of x is equal to 4. And so we can actually just plug that in over here. This becomes 4. Now to finish up this question, what we're going to do is plug in 5 and then subtract what we get when we plug in the number 1. So we get 25 over 2 minus 1 over 2 plus 4. Well, this becomes 24 over 2 plus 4. That's just 12 plus 4, giving us our answer, which is 16. Okay, so that's the answer for this example. All right, practice. Let's start with a function we're going to call f of x sine of x cubed. And our goal here for this first part is to determine the range of this function. Okay, we want to find the range of f of x if it's sine of x cubed. Well, to do that, we're going to start with recognizing that sine of x is going to be bounded below by the number 0, and it's bounded above by the number 1. So no matter what values we plug in here for x, the y values of sine will always be bounded above and below by these numbers. And then what we can do here is we can actually just cube this inequality. Sorry, this is greater than or equal to. We can cube this whole inequality, each individual part. So we have 0. We're going to cube this. Is less than or equal to sine of x cubed, which is less than or equal to 1 cubed. So we get 0. That's the same thing as 0 cubed. Is less than or equal to sine cubed. The notation is a little weird, but you can bring the 3 on the outside or the inside of this trig function. It just means sine cubed, which is less than or equal to 1. And so the range of sine cubed, or all the possible y values, is actually the same as the range of sine. And so that's going to be the answer for this one. So 0 to 1. Let's say we have this function here where sine cubed of x is equal to 1. And we want to determine how many solutions there are on the interval 0 to 2 pi. Okay, well, essentially what we're going to do is solve this for x. And to do that, let's take this function, and let's take the cube root of this function. Cube root. So when we take the cube root, it'll undo the cubed on the right-hand side. So sine, or on the left-hand side, sine of x, which is what we get when we take the cube root of sine cubed, is equal to 1. So the question is, how many times on the interval 0 to 2 pi, so how many times on the unit circle is sine of x equal to the number 1? So how many times on the unit circle is the y value equal to 1? Well, on 0 is less than or equal to x, which is less than or equal to 2 pi. There is one solution. So on the unit circle, if you can visualize it, the y value is equal to 1 time, and that is at 90 degrees. And so that's going to be the answer for this one. So one solution. Okay, letter B. Here's our function. This just wants us to take the derivative of this. Before we take the derivative, I'm going to rewrite it like this. And the reason why I'm writing it like this is because I think it's a little bit more clear that we're using, it provides more of an indication that we're going to be using the chain rule to take the derivative of this, if we write it in this notation. So the derivative, using the chain rule, is going to be 3 sine of x squared times cosine of x. Okay? And now just to kind of write it, so we take the derivative of the outside function that brings the 3 down and then change the 3 to the 2. The inside function stays the same. Then we multiply everything by the derivative of the inside function. And so the solution in the form that they want us to write it in looks like this. And it doesn't ask for this, but we can identify the a, p, and q values now. Well, the a value is going to be 3, the p value is 2, and then the q value is the exponent of cosine, which is 1 in this case. All right, and the last question is the applications of integral question. So let's say we have g of x, and g of x is equal to the square root of 3 times sine of x cosine of x to the 1/2. Okay, and the question is basically asking us to take this function from 0 to pi over 2 and rotate it around the x-axis. So we know that the volume generated is going to be the integral from a to b of g of x squared dx. So this is the washer method question, except that the lower function is just the number 0. So we can ignore that, and so it's just a simple, simplified version of that formula. Let's plug in this function in here into the integrand. Pi integral from 0 to pi over 2, and so we're going to take this whole thing and then square it. The square root of 3 times sine of x times cosine of x to the 1/2 squared dx. So before we try to integrate this, let's distribute this squared to all of these terms. So this is the same thing as pi integral from 0 to pi over 2, 3 sine squared x, and then cosine of the 1/2 squared is just going to be cosine of x dx. Let's factor out the 3 just to simplify this. And let's write it like this. Okay, so now we want to integrate this. It might not be that clear, but this is actually going to be a use substitution question. Okay? And the u substitution, remember the u substitutions are used when we have one term in the integrand whose derivative is located somewhere else in the integrand. In this case, the u value is going to be equal to sine. Because notice if we take the derivative, du, we get cosine of x dx, which is located somewhere else in the integrand. So now let's do the substitution. So this integral is equal to 3 pi. Well, sine cubed, you can just write as u cubed. Sorry, sine squared is equal to u squared. And then cosine dx, well, that's just going to be du. The limits of integration can be rewritten as u values by using this formula here. So I'm going to take the lower limit of integration, 0, plug it in this formula for x, and then we're going to evaluate sine of 0. Well, sine of 0 is 0, and so the lower limit of integration is 0 in this case. The upper limit of integration is going to be what we get when we plug in pi over 2 for x. So sine of pi over 2, that's the y value at 90 degrees on the unit circle, and that's 1. So to integrate this now, we're just going to integrate everything in terms of u. So this becomes u cubed over 3, evaluated from 0 to 1. And so now the 0 term will go away. All we have to do is plug in 1 for u and then simplify to get us our answer. So we get 3 pi times 1/3. This is just going to be pi. And that's our answer. All right, we're going to wrap up this video by going through this problem set number 1. So another application of integration question is when we have to find the area between the curves. In this case, we have two functions, 1 over x and then k over x, and they form two regions, A and B. And what we're going to do here is we're going to determine the region of area A, and then the region of area B, and then question C wants us to find the ratio of these two regions. Okay, so the first thing we're going to do is let's recognize that when we are finding the area between two curves, we're going to do the upper function minus the lower function. So the region A is equal to the integral from 1/6 to 1 of the upper function, k over x minus the lower function. Okay, and let's integrate this. Well, this will become k natural log of x minus the natural log of x, evaluated from 1/6 to 1. Now if we plug in 1 here, we get 0 minus what we get when we plug in 1/6. Okay, and let's just rewrite this. Well, this is the same thing as negative natural log of 1/6 raised to the k. This k can come to the exponent here. Minus the natural log of 1/6. And we can combine these together by using a property of logarithms, that when you subtract two logarithmic expressions, you can divide the functions or the terms inside the logarithm. So this becomes 1/6 to the k over 1/6. The absolute value signs don't really matter here, so we're going to get rid of them. So we end up with negative natural log of 1/6 raised to the k minus 1. Okay, and the last thing we're going to do is let's bring the k minus 1 to the outside, and we get, this becomes 1 minus k, natural log of 1/6, and we're going to leave our answer like that for this one. Next one wants us to find the area of region B, which is going to be the same thing, except the limits of integration are going to be different. So in this case, instead of 1/6 to 1, it's going to be 1 to the square root of 6. Okay, so we have k over x minus 1 over x dx. And now the integral of this is k natural log of x, same as before, minus ln of x, evaluated from 1 to the square root of 6. Well, in this case, the 1 term is going to be second, and so we're just all I need to do here is plug in the square root of 6. So k natural log of the square root of 6 minus the natural log of the square root of 6. Now let's simplify this. So this becomes the natural log of square root of 6. Again, I'll get rid of the absolute value signs. Natural log of the square root of 6 raised to the k power times the square root of 6. And now we can finish up this question by first rewriting it like this. This becomes the natural log of the square root of 6 to the k over the square root of 6, which is the natural log of the square root of 6, k minus 1, and then lastly the k minus 1 can factor out to the outside using that property of logarithms. Okay? And the reason why we want to write it like this is because it's going to help with the last question, which wants us to find the ratio of a to b. So if I want to find the ratio of a to b, let's just plug these values we got into the left-hand side and the right-hand side of this statement here. So the ratio a colon b. 1 minus k natural log of 1/6 colon k minus 1 natural log of the square root of 6. Well, let's do two things here. I'm just going to rewrite the expressions inside the logarithms. Instead of 1 over 6, let's write 6 to the negative 1. And then instead of the square root of 6, let's write 6 to the 1/2. Okay? So what we can do here is now let's bring these two statements outside of the logarithms. We can bring these outside of the exponents and multiply them on the outside. So if I bring out this negative 1, this becomes k minus 1, flips the order, natural log of 6. And if I bring out the 1/2, I get 1/2 k minus 1, natural log of 6. And the reason why we're doing this now is because notice that the k minus 1s will cancel. So will the natural log of 6 values. And so the ratio of a to b is 1 to 1/2 or 2 to 1. Okay, and so that's the answer for the last one.